In this video, we are asked to show that this integral is equal to pi over 2 times secant of pi a over 2. So we are going to start with a u sub, right? So we are going to let u to be equal to x squared, just this, right? So that implies that x is equal to u raised to the power 1 over 2. So here dx is going to be 1/2 u raised to the power negative 1/2 du. Alright, now what about the change in limits? When x is equal to 0, that is the lower limit, u is going to be 0 squared, which is 0. And when x is equal to infinity, the upper limit, u is infinity squared, which is infinity. And now the integral in the u world will look like this. I is equal to the integral, the limits will not change, from 0 to infinity of x raised to the power a. X is u raised to the power 1 over 2. So u raised to the power 1/2 raised to the power a divided by 1 plus x squared, and x squared is u, multiplied by dx, and dx is 1/2 u raised to the power negative 1/2 du. Cool. So here I is equal to 1/2 is a constant, comes in front here. And we have the integral from 0 to infinity of u raised to the power a over 2. And this is multiplied by u raised to the power negative 1 over 2. All this one divided by 1 plus u du. And this is equal to 1/2 the integral from 0 to infinity. Combining this using the laws of indices, that is going to be u raised to the power a minus 1 all over 2 divided by 1 plus u du. Cool. And now we are going to compare this one to the beta function, right? So let me write it here. The beta function, if you have the beta of these complex arguments m and n, this is the same as the integral from 0 to infinity of x raised to the power m minus 1 all over 1 plus x raised to the power m plus n, like this, and then dx. This is the beta of m and n. So we are going to rewrite this one to look like the beta function, right? So now let's do the comparison. So in doing the comparison, we have this a minus 1 over 2 is the same as m minus 1. We are trying to find m and n here. So a minus 1 over 2 is the same as m minus 1. So we have a minus 1 over 2. This is the same as m minus 1. So we can find m. M is equal to 1 plus a minus 1 over 2. And that is equals to what? 2 plus a minus 1 all over 2. And that is equals to 1 plus a over 2. So we have found m. M is equal to 1 plus a over 2. Let's find n, right? Be mindful that this 1 plus u is 1 plus u raised to the power 1, right? So when we are doing the comparison, this is what we have. We are going to equate m plus n here to be equal to 1 because the exponents must be the same, right? So here we have 1 to be equal to m plus n. So we have already found m, so we have to find n. N is equal to 1 minus m, and that is equal to what? 1 minus, in place of m, we have to write 1 plus a over 2, like this. And this is equals to 2 minus 1 minus a, all this 1 over 2. And that is equals to 1 minus a over 2. So the value of n is 1 minus a all over 2, like this. Now that we have found m and n, we can now write the integral to look like the beta function. So our integral I is 1/2 in front, the integral from 0 to infinity of u raised to the power, I want to write this one to look like this, right? So that is going to be m minus 1. We have found m to be this. That is 1 plus a all over 2 minus 1, right? All this one divided by 1 plus u raised to the power 1, but 1 can be written as m plus n, as in the beta function. So m plus n here is going to be 1 plus a over 2 plus n, and n is 1 minus a over 2. Just summing these ones, right? And then du. All right, so this is how we can rewrite the integral. And now if we compare this one to the gamma representation of the beta function, beta of m and n, this is the same as the gamma of m, the gamma of n divided by the gamma of the sum m plus n, right? So in our integral here, this one is equals to 1/2 the beta of m. M is 1 plus a over 2, and n is 1 minus a over 2, like this. So these are our arguments for the beta function. And now that we have this, our integral I is going to be equal to 1/2. Now using the gamma representation of the beta function, that is going to be equal to the gamma of 1 plus a over 2 times the gamma of 1 minus a over 2, like this. All this one divided by the gamma of the sum, that is 1 plus a over 2 plus 1 minus a over 2, like this. Alright, all multiplied by 1/2. Alright, cool. So I is equal to 1/2, and then what do we have? We have the gamma of 1 plus a over 2, and then the gamma of 1 minus a over 2. All this one in parentheses, and divided by the gamma of the sum. When you sum the m and n, that is going to give you 1, right? So you have gamma of 1, because summing these ones will yield 1, that is 2 over 2. And now what do you have? Gamma of 1 is the same as 0 factorial, and 0 factorial is 1. So gamma of 1, sorry about this, gamma of 1 is 1, and that is equals to 1/2. And then we have the gamma of 1 plus a over 2. This is multiplied by the gamma of 1 minus a over 2, like this. So this is what we have left. And now we know that this one, 1 minus a over 2, this is the same as 1 minus 1 plus a over 2, right? So this one is just 1 minus the other one. So I'm going to rewrite the integral like this. So the resulting value of the integral is 1/2, and then we have the gamma of 1 plus a over 2, and this is multiplied by the gamma. Instead of writing this, I am going to write the whole of this, and that is going to be 1 minus 1 plus a all over 2, like this. So this is what we have. And now we have to compare this one to the Euler's reflection formula. So we have the Euler's reflection formula, Euler's reflection formula, Euler's reflection formula. So when we have this, the Euler's reflection formula states that if we have the gamma of, let's say, a number z times the gamma of 1 minus z, this is the same as pi all over sine of pi times z, right? So because we have this and the gamma of the other one is 1 minus this one, we can use the Euler's reflection formula to solve it, right? So what is z in this case? Z in our case here is equals to 1 plus a all over 2, if we compare that one to the Euler's reflection formula. Alright, so I here is equal to 1/2, and I'm solving that using the Euler's reflection formula. We are going to have pi all over sine of pi times z. What is z? Z is 1 plus a over 2 in our case. Alright, so I is equal to 1/2, and then we have pi all over sine of, now multiply in with the pi, we are going to have pi over 2 plus pi a over 2, like this. So we can now use the double angle identity, right? So you have the double angle identity. If we have the sine of pi over 2 plus the pi a over 2, this is the same as sine of pi over 2 cosine of pi a over 2 plus sine of pi a over 2, and then cosine of pi over 2, like this. This is from the double angle identity. So this is equals to sine of pi over 2 is 1, and that is going to be left with the cosine of pi a over 2 here. and cosine of pi over 2 is 0, and that is going to be 0 there. So in the end, this is going to evaluate to cosine of pi a over 2. So this is the same as the sine of pi over 2 plus pi a over 2. So in place of this, I'm going to write that. Alright, so the integral will now simplify to this. This is 1/2, and then so this will now be pi over 2, right? I'm going to bring the pi out, so pi over 2, and this is multiplied by 1 all over cosine of pi a over 2, like this. And in the end, we have this. So if 1 over cosine is a secant, then 1 over cosine of pi a over 2 is this, the secant of pi a over 2, like that. So this is the proof that we are asked to find. So I is evaluating to pi over 2 times secant of pi a over 2. And that is by courtesy, the beta function and the Euler's reflection formula. So that is how I solved this integral. If you really find this helpful, please give me a thumbs up and subscribe to Calculus Diaries for more engaging content. I thank you so much for watching this video, and I will see you in the next one. Bye bye.